And it's my pleasure to introduce today's special seminar, and the speaker is John Lawhead. John is a philosopher. He's a graduate from Berkeley with a degree that includes something about peace and
I'm glad you remembered that.
Love and peace. And then a PhD in this area, PhD from Columbia University in New York in philosophy on a number of subjects related to the philosophy of science, and in particular the philosophy and ethical questions involved in aspects of climate change, which comes back to a geology department or sciences. We in our sciences feel as though in many ways we own climate change because we've been studying it for millennia, billions of years in fact. But of course, the climate change relevant to international relations students and many environmental studies students has to do with the climate change that's occurring today. And so with respect to climate change and the ethical choices involved in mitigating climate change, that's the subject that John's going to be talking about. But as a shameless plug for my department and a new course that you might look into if interested, the course number is 351. It's a modestly upper level. The point being, what we're doing in our sciences is trying to attract students like you who might be interested in the science of climate change and issues involving climate change. Issues that may be political, issues that might have to be resolved through a diplomatic sort of relationship, issues that may in fact be ethical, as John is going to speak to, philosophical if you will. But what we wish to do with this course and with this minor path is to explore bridges between the science of climate and the science of climate change and these other topics. So just spread that news if you think it's relevant to either you or your close friends and colleagues. So back to the speaker at hand, the philosophy of science and ethical choices regarding geoengineering is the subject of today's talk. So with no further ado, welcome, John.
All right. Thank you, Will. Yeah, so I'm a philosopher. I'm kind of curious to get started what everybody's background is here. Some of you I know this was originally pitched as an international relations type talk. So how many of you are like social science-y oriented?
IR?
Yeah, or international relations, something like that. And how many of you are like hard science, like physical science, geoscience, something like that? And then the rest of you are something else entirely, humanities. Any philosophy people here other than Rafe? Okay, good. So the project that I've been doing most of the time since I've been here has been focusing on geoengineering, as Will said. Geoengineering is one of the lesser explored areas, I think, when it comes to dealing with climate change. You'll see as I kind of get talking, in some of the areas, the research is so thin that there's almost nothing at all to say, which is sort of worrying because more and more this is starting to be taken seriously as the kind of thing that we might have to employ if we keep not dealing with climate change through other avenues. So it's an area that's really ripe for philosophical exploration. There's a lot of interesting foundational issues that we can talk about, and it's also something that's obviously relevant to people who are in geosciences and people who are interested in like international governance and that sort of thing. The solutions that are going to be deployed in this area are the kinds of things that really nobody's ever tried to tackle before and are going to require a kind of governmental framework that's unfamiliar and that's really never been tried in the history of society or science. So I want to start just by sort of contextualizing where geoengineering fits in with other kinds of strategies for dealing with climate change, the kind of stuff that you're probably more familiar with. So the kind of strategy that most people know, if you go out on the street, if you go out on Hollywood Boulevard and start talking to people about climate change and asking them what we should do about it, the kinds of, insofar as people are going to say you should do anything about it, the kinds of answers that people are going to give usually revolve around what's called mitigation. So mitigation is policies that are designed to sort of stop climate change or reverse the trajectory that we're on before it actually gets rolling, before we can do any further damage. These are the policies that are really familiar to everybody. They usually involve intervening on human behavior, doing something to change the way that we're producing energy or how we're conducting our economy, something like that, so that we can prevent further damage. So examples, stuff like carbon tax, which some of you are probably familiar with, especially people who are IR-oriented. Things like cap and trade, alternative energy research and development, so figuring out how we can power the international economy and human civilization without resorting to all these fossil fuels, that sort of thing. This is the gold standard of climate change response. This is the kind of thing that, as Will said, the geologists and the earth scientists have been talking about for geologic ages. The very first IPCC report focused really heavily on mitigation strategies, and all of the subsequent IPCC reports have done likewise. These are the things that the scientists are telling us we really ought to be pursuing if we want to stop this harm before it gets out of control. Unfortunately, we haven't really listened all that well. So this is the second major way that we might cope with this stuff. This has gotten more popular, especially with the sort of conservative-leaning side of things. People who have sort of free market ideology leanings, people who have libertarianish leanings sometimes are endorsing these sorts of strategies of adaptation. Adaptation involves reducing the impact of climate change, the kind of damage that it's going to do to us, that it's going to do to our civilization. Not necessarily preventing the actual climate from changing, but preventing it from being as much of a disaster as maybe it could be. Adaptation strategies are often given an economic basis. Some of you might have heard of the Stern report, which was an economic report that came out of the UK a couple of years back that was tackling exactly how expensive it would be to try to mitigate some of the damage of climate change and possibly to adapt to it, to put a number on this. The argument that people usually give in favor of adaptation is that it's going to be cheaper in the long run, so they claim, than mitigation would be. That's an open question. It's still sort of up in the air. But in contrast to mitigation, this can involve changes to either human or natural systems, so stuff like immigration plans, moving people out of the areas that are going to be most hard hit by climate change, levee construction, the kind of thing that New Orleans could have benefited from a couple of years back to prevent the sea level increases from doing damage, agricultural land use changes as places that previously could support agriculture no longer can or can only support a different kind of crop, that sort of stuff. So then there's geoengineering. Mitigation and adaptation have been pretty well explored. I would say mitigation probably more so than adaptation, though it looks more and more like we're trending toward an adaptivist angle. Geoengineering until very recently was not taken particularly seriously as a legitimate third strategy here. It was sort of fringe. The impression was that these are sort of high in the sky, science fiction-y ideas that involve us doing bizarre things like shooting mirrors up into space to block out the sun's rays. And until really the last 10 or 15 years, this hasn't gotten a whole lot of play in either the scientific literature or in popular media. There are a couple of different reasons for that. I like to think that the most optimistic one is that everybody thought that by the time we got to this point, we would have solved it. We would actually have some sort of strategy that we had agreed upon and that was on the table that would let us mitigate this stuff, and it would never come to this. But as that has continued to not happen, as we're getting closer and closer to that 2 degrees Celsius danger zone that people are concerned about, this has become more and more an object of attention. The more recent IPCC report, the one that came out last year or the year before, for the first time had a really significant section on this. There was a 50 or 60 page analysis. They convened their own special working group to talk about geoengineering. So some of you, if you guys watch Bill Maher on HBO, he had Bill Nye, the science guy, on a couple of weeks ago, maybe last month. And Bill Nye was actually talking about this, and he just said, you're all freaking crazy, like nobody would want to do this. It was a Newsweek cover story back in December. So all of a sudden this stuff, basically since I've started working here, which I take all of the credit for, has kind of exploded into popular consciousness. People are thinking about this in a way that they hadn't been in a serious way before. So for the purposes of our discussion, here's what I'm going to mean by geoengineering. I'm a philosopher, so we have to give a lot of definitions of things. Geoengineering is deliberately pursued as a response to climate change and not as a side effect of another activity. So if we do something like, I don't know, set off a nuclear weapon, or if Iran bombs somebody and kicks up a whole bunch of dust into the atmosphere and we get a nuclear winter, that's not going to count as geoengineering on this view. I'm interested in stuff where we're doing this sort of thing deliberately. Those kinds of interventions, but cases where we're doing it on purpose and not by accident. It's also designed to produce an effect that's global in scope and capable of impacting the climate on pretty long time scales. for this to be a serious option, it's going to have to be at least years, because that's how long it's going to take us to sort of step things down in terms of mitigation or adaptation. So doing something like erecting a biodome out in the Mojave Desert and then going and living there, even though it's changing the climate for a long term, very locally, that's not going to count for the kind of thing that I'm interested in either. And the third definition primarily involves interventions in the functioning of geosystems rather than human institutions, behavior, or other kinds of natural systems. Just yesterday I saw there's a new paper up on the archive. For those of you who are science people, you know what that is. It's a preprint server where people put up their publishing papers before they go to print, where some people at one or another complex systems institute, I think it was in New England, proposed that we could do genetic engineering and build new and better bacteria and release them into the world. And they would uptake carbon dioxide in a way that was more efficient than some of the bacteria that's around right now, and that would help things out. So that's a kind of geoengineering, but it's not the sort of thing that I'm interested in here. I'm interested in cases where we're intervening on climate systems or geosystems directly. Doing things like genetically engineering humans to be smaller and use less oxygen or something like that, which Newsweek, that was one of their proposed solutions, which was really bizarre. That's also not going to count here. That clear? Okay, some pictures. So this is the carbon cycle, which some of you who are earth sciencey people might be familiar with. This is the global sort of circulation of all of the carbon and carbon-containing compounds as they move around in the biosphere and on land, in the ocean, and through human activity. The numbers in black are the natural sort of migration, the natural kinds of forcings that take place in the absence of human activity. So on a yearly basis, this is all given in gigatons of carbon, or gigatons per year, which is a lot. We have like 70 and a half moving from the surface of the ocean into the atmosphere. Fossil fuels have about 3,700 gigatons stored, that sort of thing. So this should give you some idea of the kinds of places that we might be able to intervene if we're interested in geoengineering. The red numbers are the numbers that are anthropogenic additions. So that's the changes that are happening as a result of the kinds of stuff that we're doing, either as industry or agriculture or whatever. So we're taking about 244 gigatons out and pumping them out to various places as a result of our activities. One of the interesting things to notice here is that the deep ocean and the intermediate ocean, plus the surface ocean, has several orders of magnitude more carbon or carbon dioxide stored in it than the atmosphere does. This is the kind of thing that I think surprises people a lot of times, because most of the time when you're hearing about this stuff, you hear about atmospheric carbon content and carbon dioxide and greenhouse gases going up into the atmosphere. But really, I mean, that's important, but the vast majority of the carbon that's on the planet is locked up in the deep ocean and then in plants and animals and whatnot up on land. That's an important point that we're going to come back to, because the ocean has a really big role to play here. But this is just supposed to give you an idea of the kinds of places that we can press on this. Mitigation, right, mostly focuses on decreasing this. But if you look at other places where the numbers are big, you can sort of imagine the sorts of interventions that we might make to try to press in the right direction and get rid of carbon dioxide or the like. This is just a really short table that summarizes pretty much what I just told you, just to get it in your heads what the relationship between geoengineering and mitigation and adaptation are supposed to be. Human behavior and natural systems on one axis, and then 3 ways that it might help us on the other axis. So either preventing climate change, preventing climate-related damage, or preventing global average temperature increase, which is not exactly the same as these two. Some of you probably know, right, that global warming, right, the term that people tend to use, is sort of a misnomer, because that's not the only sort of thing that's going on here, right? We're talking about ocean acidification, changes to ecosystems, all sorts of different tweaks that are happening to global systems as a result of the kinds of activities that we're doing. So this just gives you an idea of how to contextualize stuff. All right. So geoengineering, this third way that we've been talking about, can roughly be divided into 2 sorts of categories, 2 broad kinds of approaches that we might take. The first one is solar radiation management. Insofar as people are usually familiar with geoengineering, maybe just because this is the craziest one, my experience is that most people have heard about space mirrors. Have you guys heard about this approach? Yeah, some people have. So the one that gets a lot of play in sort of the popular imagination because it's really evocative is this idea of sending large reflective surfaces up in between the Earth and the Sun, putting them at the Lagrange point, which is the point between two objects where they'll be steady, and then they'll throw some shade, as it were, our way, reflect some of the sunlight back. That's a kind of solar radiation management, but it's not the kind of solar radiation management that I'm particularly interested in talking about here, largely because it's completely unrealistic. It's not the sort of thing that we would be able to deploy in any kind of timely fashion. So I'm going to focus on two, aerosol injection and albedo management. Let's start with aerosols. So this is probably, if space mirrors are the ones that capture people's imagination, stratospheric aerosol injection is probably the one that's most popular in the scientific literature. It's the kind of geoengineering that, if you talk to somebody who knows something about this, is the one that they're probably going to come up with and talk to you about for a variety of different reasons. This is what this sort of approach is going to look like. So here's the sun, right, shooting rays down into the atmosphere. As I'm sure you're aware, that's a large part of what heats the planet. If we didn't have the sun, there would be no heat. What we can do, it turns out, is using blimps, I guess. I don't know why blimps and not airplanes, but every time I see this depicted, it's blimps. Maybe they're cooler. Go way up above where the weather is, way up above where natural clouds are, and pump a bunch of what's called aerosols into the atmosphere. Aerosols in the scientific sense are pretty much exactly the same kind of thing that you think of when you think of like the colloquial use of aerosols. So if you have hairspray or whatever, it's really fine drops of a liquid, something on the order of about half a micrometer in diameter, so half of a millionth of a meter, suspended in some gas, so a really fine mist. Sulfur compounds, it turns out, are particularly good at reflecting sunlight when they're way up in the upper atmosphere. So the idea is to use these blimps, pump out a whole bunch of these aerosol particles, pump out this really big fine mist, probably over the equator, and then let sort of trade winds and natural atmospheric circulation transport this stuff all over the place, so we blanket the planet in this mist of sulfuric compounds. The idea here is that then that's going to reflect a lot of the sunlight before it actually has a chance to make it down into the lower atmosphere. And the result of that is that the temperatures are going to go down because the energy isn't going to be able to make it far enough down to get trapped by the greenhouse effect. The two compounds that people tend to think about using most often are hydrogen sulfide and sulfur dioxide, and there's a good reason for that I will get to in a moment. So here's some projections of what this might do. This is drawn from the most recent IPCC report. There's two scenarios here. A and B are one linked scenario, and C and D are another linked scenario. This is a temperature anomaly scale given in degrees Celsius. The A scenario is what the projections are going to look like if we keep going on the same path that we're going when we get to about a doubling of CO2 over pre-industrial levels. So as you know, and as you can see, things are going to warm up quite a bit. So in the absence of any kind of intervention, doubling the CO2 count in the atmosphere over pre-industrial levels is going to heat the planet up really, really significantly. This is something that everybody's already familiar with. And then the gray is places where there's a statistically significant change, where this is going to make a meaningful impact on the planet. So basically everywhere, right? There's some dots. I'm not sure why those dots are there. But pretty much everywhere in the absence of any kind of intervention. C and D are exactly the same scenario, so we still have a CO2 doubling. But now we've done this solar radiation management strategy. We've released a whole bunch of sulfur dioxide, aerosol particles into the upper atmosphere, given them a chance. It takes about 6 months to blanket the planet once we've released it. And now the temperature map looks a whole lot better, right? There's this big band right around the equator where there's really not much of a temperature anomaly at all. The proposal is so effective right around the equator because that's where the angle of incidence, right, where the solar radiation is coming most intensely, so the reflection is really, really effective there. There's still some temperature change, especially around the Arctic and the Antarctic, but it's the kind of thing that we can deal with. It's probably right about where we're at right now, actually, so we could kind of freeze things where we're at with this proposal. Again, there's some significant change in that scenario, but it's a much, much better looking scenario. And again, it doesn't require us to actually do anything, which was the attraction for a lot of people in terms of mitigation. We don't have to stop burning fossil fuels, right? land use changes emitting carbon dioxide. This is just entirely through the release of the sulfur dioxide compounds. One of the downsides is that it's going to take a whole lot of these sulfur dioxide compounds, about 5 to 7 teragrams every year pumped up into the upper atmosphere, which is a whole lot. If you think of like bytes, gigabytes, terabytes, right? That's a lot of sulfur dioxide. So this is the kind of thing that we can't just sort of do it and then walk away. It's going to require a sustained investment. The residence time for these compounds is somewhere on the order of 18 months before they start to precipitate out and rain out of the atmosphere. So once we start it, if we want to keep maintaining those effects, we're going to have to keep those blimps up and pumping more of this stuff out all the time. We would need about a 2% decrease in the insulation for every CO2 doubling. So if we keep burning stuff, we're going to have to keep doing this and more and more and more every year, which is another one of the problems. So let's look at some of these issues now that we know how that works. One of the reasons that this proposal is so attractive to begin with is that it's one of the very few instances of geoengineering where we have an existent natural model. This is Mount Pinatubo. Some of you might remember this happening, but most of you look too young. This was in June of 1991. Mount Pinatubo was one of the biggest volcanic eruptions in recent history. The only one that was bigger that's taken place in the last couple hundred years was Krakatoa in the 1800s. Mount Pinatubo released tons and tons of stuff into the upper atmosphere, soot, there was magma, greenhouse gases, but it also happened to, because of the kind of volcano that it is, happened to release a lot of these sulfuric compounds, which is very interesting because it gives us some idea, without having to sort of lay everything on the line and do this ourselves, it gives us some idea of what things would look like if we actually pursued this strategy. So, oops, that one. We got, as a result of Pinatubo's eruption, it released something like 8 teragrams of sulfuric compounds, so right around actually the amount that we're thinking of doing. We got a global temperature drop of 0.5 degrees Celsius for 2 years, which doesn't sound like much, but that's a really big deal. That's a lot of heat energy that's not coming down onto the planet, that's getting reflected out of the atmosphere. I mean, if you think about the projections that people talk about in like the IPCC, we think that about 2 degrees Celsius over the pre-industrial maximum is starting to risk catastrophic changes. In light of that, 0.5 degree, that's a quarter of the change, right? So it's a really big deal. These numbers don't seem very high, but that makes a big difference. But a temperature drop wasn't the only thing that we got, unfortunately. I've been sort of talking about this sulfuric aerosol plan as if it's wonderful and we should all pursue it, but there were a lot of problems with this as well. Most significantly, we got a whole bunch of droughts all over the world. So this is from a paper in 2007 by Trimberth and Dye. This is, the solid line is freshwater discharge, so runoff from lakes and rivers, and the dotted line is land precipitation, so the amount of rain that fell over land masses, not counting the rain that fell over the ocean. Pinatubo erupted right there, and look at what happened. For about the same amount of time that we got that temperature decrease, precipitation around the world plummeted. There was a huge catastrophic decrease in the hydrological cycle. Again, this is really, really significant. The units that they're using, SV, which is really confusing because that's also the SI unit for radiation, but it's, in this case, it's Svengrubs. Is that how you say it? Sphere? How do you say it? Svergrubs, named after a Swedish oceanographer, I believe. Norwegian? Thank you, Julian. One of those, roughly, I guess, is the amount of it's a measure of freshwater motion, or of water motion. About 1 Svengrub is the amount of water that moves from land rivers into the ocean every year. So it's a tremendous amount of water. Look at the drop, right? We went from about, what is that, maybe 1.18 before Pinatubo erupted, all the way down to about, probably about 1 in terms of overland precipitation. That's very, very bad. That's a lot of water that should have been coming down that wasn't coming down, and it had predictably catastrophic impacts on agriculture, as we can see. So this is the Palmer Drought Index for the same years, that same 1991 to 1992, so this overlaps directly with the time that we got the temperature decrease. The Palmer Drought Index is a really complicated measure that takes a lot of different things into account. It's basically how bad of a drought is happening. It takes into account temperature and how much moisture is in the air and how much precipitation there is. Incidentally, we're about there in Southern California, so in very bad shape. This is the impact that Pinatubo had over the 1991-1992 period. A couple of interesting things to point out. One of them is that it's not at all uniform, right? So there's this big chunk of Mexico and the southwestern United States, a big chunk of South America, some places in Africa and Asia, where things actually got better. We got more precipitation than we would have, we think, in the absence of Pinatubo. Doing these sorts of calculations is a little bit complicated because there are other things that are happening all the time in the Earth system. But this is the sort of normalized picture. So they tried to subtract out the impact that this was a strong El Nino cycle, so they tried to subtract out that impact. A couple of different cyclical things that they think also would have contributed to this. So this is in the absence of all of that stuff. So there's a really strong regional component, right? Some places do very, very bad. Africa, Southern Africa, Sub-Saharan Africa, the northern part of South America do incredibly bad up in Canada. Really severe droughts. Other places either don't do that badly or actually got more precipitation. This might seem like it's sort of an ameliorating factor, but it's really not. This makes things much, much worse because there's such a strong regional component that we can't make concrete adjustments over the entire globe in terms of global policies about whether or not it's going to be a drought season or increased precipitation. The effects are all over the place. And remember, Pinatubo released just about the amount that we're thinking of releasing every year to tackle this sort of approach. So you can imagine what this sort of map is going to look like after 4 or 5 or 6 or 10 years of pursuing this sort of strategy. It's very likely, or at least very plausible, that in this case at least the cure could be worse than the disease. That implementing this sort of program, even if it drops the temperatures, is going to have such a disastrous impact on precipitation that we're going to get widespread famines, crop failures, all sorts of terrible things happening. So this is just to say that you shouldn't take my sort of quasi-enthusiastic endorsement at the beginning of this of stratospheric aerosol injection at face value. We have a natural model for this, and that's in contrast to, as you'll see, a lot of the other strategies. And what the natural model suggests is not very good. So that's also not all. Things get even worse from there for aerosol injections. These sulfur compounds are also horrible for the ozone layer. Some of you may also remember the ozone hole, though many of you look too young for that too. That's just now starting to close because we actually were able to, for once, come together as a species and do something useful and ban these sorts of compounds. This would set it back by about 70 years. The increased water vapor that's not raining out is also a greenhouse gas, so it's going to offset some of the gains we get from this. Perhaps most importantly, especially from Will's perspective, this doesn't do anything about ocean acidification or any of the other impacts of climate change. And that's why at the beginning I was so careful to distinguish that, just acting on the temperature from other kinds of climate interventions. While this will decrease the temperature, all of the other things that are happening as a result of climate change would be left the same. So this gives us some pretty good reason to think hard and long about whether or not this is the kind of strategy that we might want to pursue. What about other kinds of things? The other big strategy for solar radiation management that doesn't involve space mirrors is albedo management. Albedo, for those of you who are not geoscience-y people, is a dimensionless quantity that measures the amount of radiation that gets reflected, solar radiation that gets reflected back off of some object. So things that are very, very white, like snow, are going to reflect a lot of light, and so they don't heat up as much. Things that are dark, like asphalt, or plants, or ocean water, are going to absorb a lot of energy, and they'll heat up more quickly. This is one of the things that contributes to things like urban heat islands, right? It's warmer in cities in general than it is in the country because asphalt absorbs a lot of radiation. So this just gives you an idea of some of the spread of some different substances. So one of the ways that we could potentially intervene here is by directly trying to change the albedo on the surface of the Earth. The aerosol injection is a kind of albedo management, but it's taking place up in the atmosphere. You might think also we could try to do something down here. France, actually, I just saw the other day, is instituting some sort of policy where new buildings are going to be required to be painted white. on their roofs when they construct them, which sounds sort of weird, but it actually has a non-zero impact. It's not hugely significant, but it's something. So rather than just having bare concrete roofs, you paint it white, it reflects some more sunlight off, things don't heat up as much. We would need something like a forcing of about -4 watts per square meter to offset a CO2 doubling. We would need to decrease the energy coming in by about that amount. Again, that doesn't sound like much, but that's a fair amount of energy if it's spread over the whole planet. So this means increasing the global surface albedo from about 0.02. That's so low because we're mostly ocean, and oceans absorb a lot of energy. So up from 0.15 to 0.17. We can't do much with the ocean, though. You can't paint the ocean white. You can't really do anything at all with the ocean. So most of this intervention would have to take place on land, so we'd need a surface albedo change of about 0.08, which is not negligible. So this could take a lot of different forms. There's painting things white. Another proposal that I've seen involves planting rooftop gardens. New York has pursued this a little bit, so that rather than concrete or asphalt, you have greenery up on the roofs. One of the more popular proposals involve mirrors again, but this time rather than in space, putting them out in the desert. So putting them in something like sub-Saharan Africa or out in the Mojave right over here. So you have these huge tracts of land that are covered in reflectors and pumping the energy back up and away. This is also not without its own challenges. We don't have a natural model for this in the way that we do with Pinatubo, but the physics for this kind of stuff is pretty well understood. The biggest challenge is that this is just going to be ridiculously expensive. Try to imagine how much money it would take and how much time and manpower and energy to cover the Saharan desert in mirrors. If you wanted to hire a crew of people to go out and plant mirrors every square meter, something like that, out in the desert, that's going to be a tremendous investment. Mirrors are fragile, so you're going to need to have people coming out and maintaining them. Going through a large city like Los Angeles and painting all of the roofs white is going to be a similarly large investment. It turns out by most people's estimates, this is going to cost several $1 trillion more than the estimates for just doing mitigation. So in general, probably unless one of you can come up with a really clever solution, this is probably going to not be super cost effective. Similarly, it might disrupt ecosystems. Desert things like the sun, they don't like mirrors. Putting mirrors out in the desert is going to change a lot of things in terms of plant life and animal life. It's going to pump, if you put a bunch of reflectors on the ground and you're pushing heat back up into the atmosphere, that's going to change atmospheric circulation patterns locally because of the energy that's going back up. Land use conflicts, some people want to use deserts for things other than mirror farms, et cetera. So it's not going to be cheap, it's not going to be particularly easy, and it's not going to be particularly reversible if we decided we wanted to change our minds. For all of the expense of laying out all of those mirrors or painting all of those roofs white, if something bad happens that we didn't anticipate, now you have to hire that crew to go back out and take them down, right? And that might be an investment that people are not super willing to make for fairly understandable reasons. All right, so that's albedo management. The other major track for geoengineering, the other major high-level strategy is carbon capture and sequestration. So rather than working on the incoming solar radiation by trying to change how much we reflect or putting aerosols up in the atmosphere, maybe we can operate directly on the problem rather than just on one of the symptoms and try to get rid of some of the carbon dioxide that's already out there. The most well-explored, which is saying very, very little, of these tactics is ocean fertilization. When I say the most well-explored, I mean there's a literature of maybe 100 papers out there, maybe, exploring this idea. It's not something that the scientific community has spent a lot of time on. It's not something that a lot of research money has gone into. We don't really know a whole lot about it, but this is the most explored of them. So here's what this looks like. This is the ocean carbon cycle. So we're zoomed in on that big graph or big picture that I showed you at the beginning. So there's CO2 that exchanges with the atmosphere along with heat, and then you have all these living organisms, the phytoplankton and zooplankton, and all the stuff that is resulting from them dying or whatnot, drifting down to the bottom. There's carbon dissolved in the ocean water, all sorts of lovely things. Ocean fertilization involves acting directly on the phytoplankton. So phytoplankton are things like algae. They're ocean plants, little microscopic ocean plants. And it turns out that one of the most significant limiting factors in how much life on this scale that the ocean can support is the presence of various nutrients. So phytoplankton, just like people, need to take up macronutrients from their environment in order to grow and build their cell walls. Unlike people, they're fairly simple, and so there's only a small number of things that they actually need most of the time. Nitrogen, phosphorus, and iron are the big ones that are of interest to us. So their growth is limited by this availability, by how much is in the water, how much they can take up. So maybe we can dump some of these nutrients into the water, get them to sort of bloom, and then, as all plants do, as they photosynthesize, they take up carbon dioxide and pull it out of the atmosphere. So there's iron going into the ocean. This is what's called the Redfield ratio, or Redfield number, the biologists talk about. This is the ratio of different essential nutrients in some living thing. For most phytoplankton, so it's carbon to nitrogen to phosphorus to iron, the ratio is about 106 to 16 to 1 to 0.001. That means that for every carbon particle that gets incorporated into their biosystems, into their cell walls or whatever, theoretically, it locks up about 100,000 atoms of carbon for every atom of iron that you add to them. I say theoretically because in practice, as is so often the case with this stuff, things are not at all that simple. This looks really good on paper, right? And the idea is that we could just sort of take some of these nutrients that are limiting their growth, pump them into the ocean. Now it's not a limiting factor anymore. You get a big algal bloom, and they pull out all of the carbon dioxide. But in practice, things are not that easy. One of the most significant things that you have to think about is even if it locks up 100,000 carbons for every little iron particle that you give them, how much of that actually stays locked up, right? So if you go back and look at this thing, this is a big cycle, right? It doesn't just end here. All sorts of different things are happening in the ocean. Zooplankton are eating the phytoplankton. They're dying. Their feces are dropping down. What we would want to happen here in an ideal case is that the phytoplankton pulls the CO2 out of the atmosphere, and then they just sort of drift down when they die and form all this sediment down at the bottom, and then the carbon's locked up. It can't do anything to us. It can't get back up into the atmosphere. Eventually, maybe it turns into fossil fuels, but for now, it's just sitting down there at the bottom of the ocean. But because of all of these interactions in there, that's not necessarily what happens. The phytoplankton are going to take up all of this carbon, but then a lot of them are going to get eaten by zooplankton. Zooplankton are animals like we are, which means that they respire out carbon dioxide and use oxygen. So a lot of these are just going to end up sort of getting passed through this chain, eaten by little zooplankton. The zooplankton breathe out, and the CO2 is back into the cycle again. It's not locked up. And it's actually very difficult to figure out exactly how much of this is going to transpire because we have no natural model. We don't know what a bloom like this is going to look like. We don't know what the effects are going to be. The other big problem is what they call downstream nutrient robbing. So if we decide that, say, iron is the most efficient way to do this, we put a bunch of soluble iron into the ocean, get a big phytoplankton bloom right where we dumped in that iron. That's great, but now all of these little phytoplanktons that are growing are using up the nitrogen and using up the phosphorus that were in the area, and so things sort of surrounding them now don't have those nutrients. And so for this big bloom that you have here, now over here you're having a big die-off because they're taking their iron and also taking all of the available phosphorus and nitrogen. So a lot of people think, and again this is controversial, that if we tried this and on any kind of controlled scale, what you would get is a local bloom and then surrounded by a big ring of die-off. So obviously that's not going to be workable for the kind of thing that we want because it's just going to balance out further downstream. Likewise, some of you have probably seen like red tides and stuff like that, big algal blooms that take place in lakes and sometimes in the ocean. These can be incredibly detrimental. Not all phytoplankton are nice and play well with other animals and plants that might be around. Some of them are incredibly toxic. They take all of the available nutrients, release some sort of toxic byproduct, and now you have a big die-off of marine life. And presumably that's bad also because we like dolphins. Algae blooms. Oops. So again, this is probably not as workable as it might seem at first. In 2012, some of you probably do remember this if you were here. A businessman, I forget what the guy's name was, one of these big Silicon Valley magnates, actually drove up in his boat onto the coast off of western Canada and tried this. Like without anybody's permission or anything, he just took a bunch of bags of dissolved iron and just dumped them off his boat into the ocean. People understandably got a little bit upset about this. This is one of the things I want to come back to at the end and talk to you guys about. But the impact was pretty much what people had predicted. You got a big bloom locally, but the further you got out away from it, the more of a die-off there was. So this downstream effect really did happen. He has some sort of plan that he thinks is going to prevent that by then doing other kinds of fertilization, dumping in nitrogen or phosphorus. But that's challenging too, in large part because we use those for things, right? Iron is pretty plentiful. It's easy to get at, but nitrogen and phosphorus are important to agriculture. They're expensive. Getting your hands on these huge quantities is not going to be easy. Other people are going to fight for that. So again, maybe not so promising. All right. This is the last sort of approach that I want to talk about, and then we can think a little bit about the international relations stuff and get some feedback from you guys. So rather than the biological ocean fertilization, the last sort of major option that's on the table is called chemical carbon capture and sequestration. So rather than using organisms, this is just going to use sort of raw, I almost said inorganic, but that's not right, non-living chemical reactions to do pretty much the same thing, to pull CO2 out of the atmosphere and sequester it somewhere, manipulating the natural carbon cycle. So one of the ways that we get a carbon cycle on the planet just naturally without any kind of human intervention is through weathering. There are minerals that are out there in the world on the land and in the ocean that can react with the CO2 in the atmosphere. Lime does this, for instance, and bind it up, grab it, and incorporate it into some new chemical compound, and then it just sits there in the form of a rock or something like that, and gets stuck there for a really long time until it gets released back into the ocean or back into the atmosphere. So we can do this if we really wanted to. This is one, there are dozens, literally, of potential reactions that could do this sort of thing. This is one of the more plausible ones because most of the materials that are involved are relatively plentiful, and it is pretty efficient, right? So you just need one of that calcium silicate molecule to lock up a molecule of CO2, and that's good. Most interestingly, we already kind of do this. So some of you might be familiar with clean coal, which are coal power plants, or sometimes they do this with natural gas too, where they have scrubbers built into the smokestacks that are pulling CO2 out of the exhaust stream. Usually it looks a lot like this. They're reacting the exhaust that's coming out of the power plant with chemicals that are in these filters, and then taking the filters and putting them somewhere, either burying them. Depending on the byproduct, sometimes they'll grind them up and dump them into the ocean. I guess that is okay. So we could do it at the source, or we could do it in the air. For obvious reasons, it's a lot more efficient to do it at the source. I'm not spending a whole lot of time on that because it sort of contradicts with my definition at the beginning. That's right on the line between mitigation and geoengineering. If we wanted to do this in the open air, it's more challenging for a couple of reasons. First of all, thermodynamics, right? If the concentration of some chemical out there is lower, it's harder to get the reaction going at the scale that we need it to get going at. Associated with that is going to be a significantly increased cost. We're going to need to build like giant fans or something that can push CO2 containing air through these filters because we don't have it ready-made, concentrated into a smokestack. That takes energy, and where do we get the energy from? Right, if the answer is just burning more fossil fuels, then this is stupid. It doesn't do anything. In fact, we're going to end up losing, again, because of thermodynamics. So much more plausible is to put this sort of capture technology on power plants themselves, which is something that's been pursued to some extent, though they actually haven't had a whole lot of success at doing this at scales, partially because it makes power more expensive, and that makes people sad. So we also could do this rather than burying it or sequestering it in the land. We could use a slightly different reaction and sequester it in the ocean, such that it forms some powerful bases. This has the advantage of offsetting some of ocean acidification also, which is a good thing. That was one of the problems with the solar radiation management, remember? So if we do this reaction properly, we might be able to kind of kill two birds with one stone. You pull the CO2 out of the atmosphere and push some bases into the ocean and offset a little bit of ocean acidification. Will knows more about this. Good. So some challenges with this. First of all, it's just a chemical reaction, so it's really slow. We can use catalysts and try to speed it up, but to some extent, you're still limited by the speed at which these reactions can take place. It's also very resource intensive. These minerals are not just laying around for anybody to pick up and use on the scales that we need them. In fact, in order to make this workable, we would need to mine lime or these silicate compounds at roughly 3 times the quantity that we're now mining coal. That's a very large industrial operation, and it's the kind of thing that would take global sort of cooperation and a huge investment of money. Again, many estimates show this being as expensive or more expensive than just doing the mitigation to begin with, so it's not clear why this is super attractive. And ocean pH is something to worry about. Even if we dump in bases, we don't know exactly how that's going to work, how it's going to affect other sorts of aspects of the marine ecosystem. Again, we have no natural model for this. Making these large-scale changes is very risky because we don't have a good way of predicting the way things are going to shake out. All right. So just really quickly to summarize all of these points into a nice, neat pro and con list so you can be refreshed. We can think about how to govern this stuff. Aerosol injection, here are some pros. It's effective. It's going to work very well. We know it's going to work well. It's relatively cheap. It's responsive. Once we start it, we're going to have the effects within a couple of months. And we have existent natural models in Pinatubo. The cons, there may be significant side effects that we're not foreseeing. There will be significant side effects with regard to precipitation. It only impacts the temperature, not ocean acidification. Potentially addictive once we start this because of the long or short residence time. If for some reason something happened and it stopped, the global temperature would shoot way up to where it would have been otherwise over the course of months, which would be bad. And it has a high potential for unilateral action. Whether this is a pro or a con is part of what I want to talk to you guys about and get your opinions. We'll do that in the discussion. Ocean fertilization. Pros, pretty cheap, at least with regard to iron. Impacts both the temperature and ocean acidification. It's fairly effective. Con, potentially disastrous side effects, which is a pretty big con. We don't know exactly what it's going to do to all of the ecosystems. In general, it's not particularly well understood, especially compared to aerosols. It's fairly slow. It's not as slow as the other carbon captures, but it's not very fast either. It's going to have to work for years before we're going to see a huge impact. Again, there's a high potential for unilateral action with this, as we saw with the California business guy. Albedo. Pro is deployable right now. You can go paint your roof tonight if you want to. It's unlikely to break down, except the mirrors. We can maintain those. Potentially helpful when used in tandem. This is another thing that I want to talk to you about, maybe using a mixed system. It's expensive, not easily reversible, and only impacts temperature again. Difficult to scale up. We need a lot of mirrors. All right. So this is a kind of more robust version of that graph that I put up at the beginning. This is just kind of a nice reference to see which strategies are supposed to be involving which of these approaches. So mitigation that prevents climate change, reducing greenhouse emissions, that sort of thing. And this is from the Royal Society report, which is one of the very few major publications to study geoengineering. One of the reasons that I really like this graph, because I'm a huge nerd, is that they figured out a cool way to represent multi-dimensional data on a two-dimensional graph, which is cool. So there's effectiveness and affordability on the axes, but then the size and color of the dots mean other things. So safety, if it's red, it's very, very unsafe. Yellow is medium, green is high. And then the timeliness of each of them is a small or a large circle. I thought that's pretty cool. So the reason that the stratospheric aerosols gets the most attention is because it's way up here in this corner. It's pretty effective and it's pretty cheap. It's quick, but it's not super safe, maybe, depending on how much you care about precipitation. Afforestation, which is not one that I talked about, but which involves just doing a lot of tree planting, is one of the safer ways of going about this, but it's also not particularly cheap. And you can see how all of these are just sort of spread out here. I just thought that was a neat representation.
It seems the cheapest of them all, right? It seems the cheapest of them all.
Basically not cheap.
Right.
Oh yeah, I guess it is. Yeah, well, yeah, cheap versus effectiveness, though. It's not particularly, the ratio is not great. Okay. So the sort of discussion that I want to put to you guys now, now that you have sort of a background in the science, and hopefully people are from the international relations are here and have things to say about this, is how we might go about governing this and how we might go about implementing this in a way that's responsible on an international scale. Most of these evaluations, in fact all of them on this little chart, are based on considering these proposals in isolation. So we think about how safe it would be to just implement stratospheric aerosols, or how safe it would be just to fertilize the ocean. This gives us some information, but there may be cases, and in fact almost certainly would be cases, where implementing this is going to happen side by side with mitigation or adaptive strategies. In fact, some of the strategies that I talked about here, that's what people are actively recommending. And that might give you reason to think that things are a little more complicated than that graph from the Royal Society makes them appear. So think about this case. Suppose that we implement the stratospheric aerosol solution, and then at the same time have some sort of carbon credit. So something like a cap and trade, where you can buy carbon credits and sell them on a market to regulate your emissions, or a carbon tax, something where we're counting units of greenhouse gases emitted. Now say the United States decides to foot the bill for the solar radiation management. We build all the blimps and get all the aerosols up there. Should we now get credit for that in terms of carbon? Because it looks on the surface like that's a reverse emission, right? We're putting something up into the atmosphere that actually cools things off. That's a good thing, so now we should be able to burn more fossil fuels and heat things up more because we invested all of this, right? But it's also the case that we're not necessarily going to bear the brunt of the damage for something like that. You saw in that graph from Pinatubo, these precipitation changes from stratospheric aerosols have very strong regional effects. What that means is some places are going to get hit really hard. And if the places to get hit hard are not also the places that are bearing the other costs, it starts to get really complicated how to integrate something like a geoengineering solution into a carbon tax or a carbon credit sort of framework. If we're the ones that invest it, right, we get the credit in terms of carbon emissions, but then we also maybe get the benefit or the least harm in terms of precipitation. So it looks like the United States then is double dipping. The smaller country that gets hit hard with precipitation changes and loses all of their crops, also is not contributing to the aerosols, so now they don't get the carbon credits and they're getting obliterated in terms of droughts. This gets very complicated very fast, and that's something that people haven't really considered very much. Yeah, so how might these climate engineering scenarios interact with other climate policies to change the utility? People tend to evaluate this stuff just using a utility function that just checks how much, like what the levels of adaptation and mitigation and engineering are. But that starts to look really implausible when you think about these more complicated examples. All right, so some concrete questions that I just want to put to you guys and see what you have to say about this. What's the right regulatory model here? We don't have a good international governance framework. We don't have a good, there aren't really any existing treaties that are going to be relevant to this, that are going to tell us how to regulate this sort of thing. How might we go about building an international consensus on which technique to employ? How do we weigh these different benefits and problems against one another in a way that's like ethically reasonable and politically responsible? How can we prevent or discourage unilateral action? This is maybe my biggest worry with this. Especially with the stratospheric aerosol stuff. It's very cheap, it happens very quickly, and it's impossible to reverse once it's gotten started. If somebody were able to get, one country or even one company were able to put all this aerosols up in the atmosphere, we just have to wait for them to fall out. The potential for unilateral action with this and with the ocean fertilization is very, very high, and that concerns me. Because as soon as one state or one company decides that it's in their interest to do this, then it might well happen that they just say, screw everybody else and go for it. And that's really worrying for obvious reasons. And how can we plan for these portfolio interactions, the interactions between different strategies? What's the right way to actually work up an analysis of that? How can we think about what the utility looks like in these interactions? So I just want to get your guys' thoughts on some of that. That's all I have to say for you guys. Thank you. Thoughts on any of this, or questions also, yeah. Yes, ma'am.
So my biggest thought is that, with the geoengineering, we're not even there. There's so many places around the world that won't even acknowledge that this is an issue.
That's
so
true.
How can you even begin this conversation?
Well, I mean, I think it's a conversation that is worth having because it's the kind of thing that is being taken seriously by some people. And one of the reasons that this is different from other kinds of climate strategies, like mitigation, is that it doesn't just affect you, right? There's no way to do geoengineering on a completely local scale. So if one country, right, if the United States all of a sudden decides to take this seriously, it's going to have an impact that's going to range over the entire globe, which is true with mitigation, right? If we drop our emissions, that has an impact, but this is a much more direct one. And given that kind of thing, it seems like sooner rather than later, we ought to be thinking about what kinds of responses we would have to something like this. Like, what are the thresholds where we would go to war to prevent somebody from doing this if they decide they want to? I mean, there's potential, I hate to appeal to the trope, but there's potential for terrorism applications for this, to drop precipitation. Given the timeliness of it, even though we're not even at the point where people are taking this seriously as a problem, I think that's the right time to start thinking about how to deal with this kind of stuff, because pretty soon it's going to be right there on the horizon. Does that make sense? Julie?
Yeah, in response to that, I think that one of the biggest problems with this is that so the moral hazard associated with engineering, maybe you can comment on.
Sure.
Essentially, the idea that people want to keep that option in the back in case, right now nobody wants to do anything about global warming because there's sort of this plateau. But imagine that now
All of a sudden,
brutally
yeah.
in the 70s, and all of a sudden everybody's freaking out and want to do something about it. And now it's too late because we've been procrastinating for at least 30 years to put in place effective mitigation strategies. So now they're going to turn to say, give me a quick fix before the planet burns up. And that's why people, that's why we have to do research on this and the pros and cons of all this, because sooner or later it's going to be put in the table in a major way.
Yeah, I mean, that's good. The fact that people are not taking the problem seriously is, I think, a good reason to be having this conversation, because, like I said at the beginning, it's quickly getting to the point where this is maybe going to be the only option that's out there that's going to actually have any kind of real impact. The moral hazard thing that Julian alluded to is, this is a concept that's out of actuarial science and economics. So the idea is that if you have a policy or some force that reduces the negative impact of taking some risky action, you may be more inclined to actually engage in that risky behavior. So the fact that I have renter's insurance maybe means I'm less likely to lock my apartment door because I know that if I get burglarized, the insurance will pay for it. People talk about this with seatbelts sometimes. That was one of the big arguments against introducing seatbelts, that if you get into an accident, you're not going to die. So it's going to make people drive worse. The herpes vaccination this comes up with. This is certainly a worry with the geoengineering too, that if people know this is sort of a thing that's on the table, maybe they're going to be less likely to pursue mitigation strategies to begin with. I think that's a really important point. There's been a smidge of empirical work that's been done about this. Some people at, I think it was Leeds University in the UK, did an actual social science survey about this stuff, where they brought people in and presented them with these arguments and tried to measure how much this moral hazard concern was impacting their behavior. What they found was that there was a really strong correlation between how much of an impact the moral hazard thing had and what they thought about climate change to begin with. So people who were more inclined to deny that this is a risk were also the people who were most susceptible to this moral hazard, which sort of suggests that they're just looking for a reason to not do anything. And that sucks, but in a way that's not as bad as it could be, right? Because these are the people who are least likely to be pursuing mitigation strategies to begin with, and the people who might actually be trying to do something or be the kinds of people who are pushing through policy changes are also the people who are least susceptible to the moral hazard concern, which that's good. More work needs to be done on that. There's just been one study where they did that. Yes?
I think it would be a miracle if we could answer any of the
Yeah, me too.
Other than that, I think it's a very important set of questions and issues that, if not here, I don't know where people will talk about.
Exactly.
As somebody who does some social sciences and kind of public attitudes, I think geoengineering is a terrible term. You gotta do something about that before
It's
you even
terrible in what way? What do you?
It's kind of a combination of a sciencey thing with an ing, with engineering, and that can give a lot of people a lot of, kind of trouble thinking about this issue. But that's really kind of a minor issue. I think generally speaking, when you look at how we can try to address these issues, there are probably a few different, kind of in terms of social sciences, a few different modes of thinking. One is to look at existing institutions.
Yeah.
And if you look at existing institutions, what are the best examples? Well, the SCCC, provides kind of a structural system, and it provides also an institutional kind of COP and the kind of committees, the technical committees. And there are some examples for how they were able to overcome high highly technical issues on joint implementation, on other issues. It took a long while, and it was not a happy, process. But overall, there is some structure that could be used. The other alternative, a second alternative, is to use other institutions where countries have a higher level of commitment. So, for instance, if you think about the economic implications of some of these issues or the trade implications, and there are international institutions that are more focused on these, and where countries have a higher level of commitment to, and also kind of a higher level of concern about risk of not participating in. And so, so one route is the existing institutions relating to climate change. The second is kind of other international institutions that can be integrated, or that these issues can be integrated into some of these, of what they're doing.
So like building it into like economic treaties, is that what you're thinking of? That like if you want to sign on to the world trade or whatever, you have to, okay, yeah, that's an interesting idea.
And I think the third issue is kind of creating something that's really specific and more scientific oriented that deals with this. And for that, I think my main question might be, for that you need some leadership. I mean, for any of these, but particularly if you want to design a specific way to address these issues, you really need some leadership. And so I was kind of interested to know whether there are any current discussions or certain countries that have done more in terms of policies, specific policies on these issues, or the EU may be kind of a general good suspect place to look at. But so I was wondering a little bit about that.
So some of this stuff there, as far as I know, there are no major policy initiatives that directly address this. It falls under the purview of some existing frameworks. So the UN Treaty on the Use of the Oceans, for instance, is going to restrict that kind of iron fertilization. And the guy that did the stuff up on the Canadian coast got in trouble from that perspective. Some of the language, like I've read pieces where people are trying to argue that like some of the language in the Kyoto protocols could maybe be, if you kind of squint at it in the right way, like it's going to fall into some of this stuff. The big one is that there's no complement to the ocean regulations for atmospheres, right? Nations own the airspace that's above them. There's no sort of concept of that as a shared resource, because there really hasn't needed to be before this. There hasn't been, until climate change, really any kind of issue where this came up, where it was, we're doing something right over our heads and it's impacting somebody on the other side of the world. So I think probably the first practical step would be trying to negotiate something like that. And as far as I know, nobody has even tried to do that yet.
I mean, another structure to think about, just in terms conceptually, is kind of the Antarctica.
Yeah, good. Or space, right? Also, yeah.
I mean, so kind of commons where property rights are defined, and where different countries feel differently in terms of their rights, I would say, and access is.
Yeah. I mean, part of the problem is until really recently, everybody's just been like, "This is crazy. We don't need to talk about this." Like, and.
But I think really the moral hazard is a pretty major.
Yeah.
Significant issue, and it's a very rocky kind of way to think about progress if you have the moral hazard.
Absolutely, yeah, absolutely. Will.
I can see why there would be a lot of value for people who are IR, environmental studies and/or poli-sci, to consider the following: that global warming is very well understood scientifically to affect the high latitudes dramatically more than the mid and low latitudes. And therefore, in some sense, countries at high latitudes, especially in the northern hemisphere, are going to be subjected to temperature change. And maybe that should then give them extra votes in the way the future unfolds. Because you just saw they were 7s and we were like 1s and 2s.
Yeah.
But that's where the ice is. And when ice melts, then you've got countries with X fraction of its population living within so many meters of sea level. And as a New Yorker, when southern Manhattan gets really, really wet, the hell's going to
People can melt down, yeah.
What countries have X fraction of people living within sea level gives that country a certain level of votage. Because they're going to be, Indonesia's going to be wiped out. They vote. They get the top vote. So
That's a very interesting
how
idea,
to
but completely unprecedented
Yeah,
in terms of international
yeah. I mean, and it's the same kind of problem with this, right? Of figuring out how to count relative votes because of how you're impacted from precipitation, right? Or how much stake, like, we've usually quantified this in terms of emissions, but it might be more appropriate to think about it in a more general unit of, like, negative utility or damage, or John Broome suggested, like, years off your quality of life when he was here. I mean, these sorts of foundational questions.
In the academic setting that we're in, obviously, especially in the school that we're at, within the football conference that we reside, we need to think of the following way. If USC can reduce its carbon footprint in some manner more than another school in our conference, we get
we win?
extra football players. It's competitive in the sense where we all care. If you can frame this problem into some sort of competitive, the nature of human competitive desire is trivialized by this comment.
So,
Very, very.
So we should have an international football team, is what you're saying?
We kind of weight the small, very small, low-lying countries to gain a whole lot of power
Yeah.
over countries with more resources.
Yeah.
Yes.
That's why. Yeah. I mean, that's the challenge, right?
I guess in terms of other international structures that
Mhm.
are currently in place might have to be adapted. I think when you think about one of the leading scientific bodies, the IPCC, and what its role is in advising policy, they make findings and then
Right.
they don't directly tell the
That's right.
policymakers what to do. And with something like this, which is even more, I think, poorly understood and has even greater impacts, I think you would want scientists to be directly advising the policymakers.
Yeah.
And I don't know if that's something that policymakers would be amenable to. And so, what?
That's a really good point, and that's something I'm really interested in. Yeah.
One of the reasons why the ATC was set up this way is that it gives it more legitimacy, that it's not
Yeah.
politically motivated. And I think there's enough climate denial as it is. There's enough denial of climate science because it's supposedly we're politically motivated, and because clearly we make so much.
Obviously,
money.
yeah.
And so these arguments are always there. So imagine if you had a body that was specifically appointed to promote policy recommendations, they would have no legitimacy.
Well, then how do you implement something? How do you get the right level of scientist interaction with this? I mean, scientists or philosophers, right? Like, we're even more biased and poor.
Special reports, and you could have a special committee on geoengineering, and they could be.
Which they did.
They only looked at it scientifically, but they could have, working group 1, 2, and 3, and they could be some
Like a
scientists looking
quasi-separate
from
body.
the government perspective,
Yeah.
as they have for mitigation
Right.
and adaptation.
I mean, they sort of did that with this report. There was a working group report on it, but they're
But it was mostly slanted towards we understand what others
and right. I mean, the answer is no, basically.
80%
Yeah.
80% science and 20 or 10%.
Yeah, that's right.
Which you could bring more balance into that.
And I mean, that's part of the reason is we need more research on this stuff, right? And that's important. Yeah.
I have two quick comments. I really like the presentation. I didn't
Thank you.
know anything about it, so I
Good.
I have comments or two questions, two thoughts. First one is about the costs. I wonder whether it's not that important, the cost, compared to the consequences or the, because I mean, costs are not necessarily negative from a political science perspective. I mean, it's good for the economy or it's good for everything. So you have a new industry, so it could grow the pill and make good things. So I guess that the aspect of the cost is much less important than the other aspect.
Mm-hmm.
My second thought is about, looking at all these scenarios, I was thinking that it will be much more difficult to agree altogether about one of these scenarios than to reduce or just.
Yeah.
I know that it's not easy to find a way to mitigate the tendency, but I mean, there you have people who would have drought and others who would have tornadoes and no one ever agreed on that. You will never find a treaty to like a war. Maybe four countries in,
You're optimistic.
in the region just agree that they will have no water for 15 years. I mean, it's impossible.
That's right.
So I guess that what geoengineering might do, even if in the case of moral hazard, where in the next 5 years we need to find a solution because there is a certain. I mean, even in that condition, I guess we will never find we never agree altogether about the solution. So I guess that what geoengineering is able to do is to make us realize that probably there is no other way than mitigating things.
I mean, that's remarkably pessimistic and optimistic of you at the same time. I mean, I wish that would happen. Like, I wish everybody would come out of this presentation and be like, that's a terrible idea. Why would we ever do that? But that doesn't seem to be the sort of thing that's going on on the international stage. That, I mean, your point about costs, right, that's sort of secondary. I think if more people had that perspective, then we wouldn't be in the situation that we're in right now. Does that make sense? Yeah.
One thing, just to bring it back to the moral hazard thing really quickly, and this is something I was just thinking about. So, like, from my perspective, like, in terms of climate change, like, particularly in developed countries, there's already enough of a moral hazard to, like, not address climate change.
Yeah.
That they're not being as negatively impacted by it as they would be facing responsibility. One hazard that I think needs to be they need to be careful about with the research is, like, kind of emphasizing the sort of precautionary principle in implementing this, or else the developed countries will have even more reason to think, like, oh, like, why should we be bearing the brunt of responsibility? We can just pay in the future for something, it's like that's just something to be conscious of, not to be, like, using this research to offer easy fixes.
Absolutely. Yeah, I mean, that's the whole crux of the moral hazard, is that people are going to walk out of this with exactly the opposite idea of what I want. That, like, look, well, we'll figure it out then, and blimps. That's fine.
Alexander was in my class, last year, 2 years ago? Yeah. But every time I teach about this, I think that people are going to come away with
Like,
the idea.
why would you do that? Yeah.
You would not believe in all
I know,
people
yeah.
who say,
I know.
oh, well, actually, we do have a way out, so why not this? It's cheap.
I mean, and that's why the scientists end up saying stuff like, well, maybe we shouldn't even be researching this, right? I mean, which isn't a position that people have. Yeah. The back. Yeah.
I think also from a psychological standpoint, this fits in with our current economic model.
Yeah.
Because it doesn't require us to reduce growth and reduce carbon
Yep.
emissions. And that's why it's so widely supported by oil companies and other
Yep.
large polluters, because it's, in a way, it seems like it's a solution to the problem when it's well, like Band-Aid, allows us to keep making the same mistakes and doesn't address the root, which is obviously a terrible solution. And
I'm glad we all agree on this.
yeah, it's interesting. It's like solve one problem by creating 7 others.
Yeah.
So I think personally that it's, in order for this to be like really taken off the table and for it to not become our like final solution, we actually have to change the way we value our economy over our environment, and it's like the most, in my opinion, the hardest change to make.
Yeah.
Just thinking about growth constantly and to think about sufficiency, and that we should stop growing, and maybe growth is not best for ourselves because our planet has a carrying capacity and it doesn't support unlimited growth. And in order for us to realize that, we need to support international laws that give more vote to the people who are affected by these things rather than people who have the money. People who have money are going to get more money.
That is how it tends to go. Yeah, I think that, but that's that's like the most fundamental of fundamental shifts in political philosophy and the way that we think about ourselves. Yep.
A quick comment. Another reason to be optimistic is that, well, if you look at the climate change governance and even power in international relations, there are 3 countries who matter:
Yeah.
China, Russia, and the US. And no solution there is at the advantage of only one of these countries. So
Yeah.
there is no incentive to just settle the matter for yourself and don't care about the others. So there is a strong incentive to get all along together.
Yeah.
I think. So it's a reason to be optimistic.
And this is one of the first problems that's been the case with, right, where it's very difficult to come up with any kind of solution that's local in any way. I mean, it's going to require international coordination and cooperation on an unprecedented scale. I mean, like, getting rid of the ozone hole is the only thing I can even think of that even has ever looked something like this. Good. Thank you for optimism. It's a depressing topic. Anything else? Further questions?
I think maybe just a quick comment about optimism. I'm not very optimistic.
Me neither.
And it's kind of a really narrow, kind of small slice of optimism. It's actually coming out of public opinion surveys of younger generation.
Yeah.
There are increasing proportions that are supporting thinking about climate change as a more important policy issue than growing the economy. And to
Really?
the extent that people, in the younger generation can maintain that once they have families and they have to go to work and
Yeah.
they're not just like
Pay back
living off
school
their
loans.
Right.
then I think we stand some chance of kind of a more significant change in society.
And like sensitive to the science and stuff too. I mean, like you were saying, rather than being like primarily driven by this ideology, that they're actually paying attention to what scientists are saying. The internet, I want to think, has some role to play in that. Yeah, that's so keep remembering that this is bad and other things are good. That's the takeaway, the moral right there. All right, guys, thank you very much.
sciences, or geology, if you like. And it's my pleasure to introduce today's special seminar, and the speaker is John Lawhead. John is a philosopher. He's a graduate from Berkeley with a degree that includes something about peace and
I'm glad you remembered that.
Love and peace. And then a PhD in this area, a PhD from Columbia University in New York in philosophy on a number of subjects related to the philosophy of science, and in particular the philosophy and ethical questions involved in aspects of climate change, which comes back to a geology department, or sciences. We in our sciences feel as though in many ways we own climate change because we've been studying it for millennia, billions of years in fact. But of course, the climate change relevant to international relations students and many environmental studies students has to do with the climate change that's occurring today. And so with respect to climate change and the ethical choices involved in mitigating climate change, that's the subject that John's going to be talking about. But as a shameless plug for my department and a new course that you might look into if interested, the course number is the 351. It's a modestly upper level. The point being, what we're doing in our sciences is trying to attract students like you who might be interested in the science of climate change and issues involving climate change. Issues that may be political, issues that might have to be resolved through a diplomatic sort of relationship, issues that may in fact be ethical, as John is going to speak to, philosophical if you will. But what we wish to do with this course and with this minor path is to explore bridges between the science of climate and the science of climate change and these other topics. So just spread that news if you think it's relevant to either you or your close friends and colleagues. So back to the speaker at hand. The philosophy of science and ethical choices regarding geoengineering is the subject of today's talk. So with no further ado, welcome, John.
All right. Thank you, Will. Yeah, so I'm a philosopher. I'm kind of curious to get started what everybody's background is here. Some of you I know this was originally pitched as an international relations type talk. So how many of you are like social science-y oriented?
IR?
Yeah, or international relations, something like that. And how many of you are like hard science, like physical science, geoscience, something like that? And then the rest of you are something else entirely, humanities. Any philosophy people here other than Rafe? Okay, good. So the project that I've been doing most of the time since I've been here has been focusing on geoengineering, as Will said. Geoengineering is one of the lesser explored areas, I think, when it comes to dealing with climate change. You'll see as I kind of get talking, in some of the areas, the research is so thin that there's almost nothing at all to say, which is sort of worrying because more and more this is starting to be taken seriously as the kind of thing that we might have to employ if we keep not dealing with climate change through other avenues. So it's an area that's really ripe for philosophical exploration. There's a lot of interesting foundational issues that we can talk about, and it's also something that's obviously relevant to people who are in geosciences and people who are interested in like international governance and that sort of thing. The solutions that are going to be deployed in this area are the kinds of things that really nobody's ever tried to tackle before and are going to require a kind of governmental framework that's unfamiliar and that's really never been tried in the history of society or science. So I want to start just by sort of contextualizing where geoengineering fits in with other kinds of strategies for dealing with climate change, the kind of stuff that you're probably more familiar with. So the kind of strategy that most people know, if you go out on the street, if you go out on Hollywood Boulevard and start talking to people about climate change and asking them what we should do about it, the kinds of, insofar as people are going to say you should do anything about it, the kinds of answers that people are going to give usually revolve around what's called mitigation. So mitigation is policies that are designed to sort of stop climate change or reverse the trajectory that we're on before it actually gets rolling, before we can do any further damage. These are the policies that are really familiar to everybody. They usually involve intervening on human behavior, doing something to change the way that we're producing energy or how we're conducting our economy, something like that, so that we can prevent further damage. So examples, stuff like carbon tax, which some of you are probably familiar with, especially people who are IR-oriented. Things like cap and trade, alternative energy research and development, so figuring out how we can power the international economy and human civilization without resorting to all these fossil fuels, that sort of thing. This is the gold standard of climate change response. This is the kind of thing that, as Will said, the geologists and the earth scientists have been talking about for geologic ages. The very first IPCC report focused really heavily on mitigation strategies, and all of the subsequent IPCC reports have done likewise. These are the things that the scientists are telling us we really ought to be pursuing if we want to stop this harm before it gets out of control. Unfortunately, we haven't really listened all that well. So this is the second major way that we might cope with this stuff. This has gotten more popular, especially with the sort of conservative-leaning side of things. People who have sort of free market ideology leanings, people who have libertarianish leanings sometimes are endorsing these sorts of strategies of adaptation. Adaptation involves reducing the impact of climate change, the kind of damage that it's going to do to us, that it's going to do to our civilization. Not necessarily preventing the actual climate from changing, but preventing it from being as much of a disaster as maybe it could be. Adaptation strategies are often given an economic basis. Some of you might have heard of the Stern report, which is an economic report that came out of the UK a couple of years back that was tackling exactly how expensive it would be to try to mitigate some of the damage of climate change and possibly to adapt to it, to put a number on this. The argument that people usually give in favor of adaptation is that it's going to be cheaper in the long run, so they claim, than mitigation would be. That's an open question. It's still sort of up in the air. But in contrast to mitigation, this can involve changes to either human or natural systems, so stuff like immigration plans, moving people out of the areas. They're going to be most hard hit by climate change. Levee construction, the kind of thing that New Orleans could have benefited from a couple of years back to prevent the sea level increases from doing damage. Agricultural land use changes, as places that previously could support agriculture no longer can, or can only support a different kind of crop, that sort of stuff. So then there's geoengineering. Mitigation and adaptation have been pretty well explored. I would say mitigation probably more so than adaptation, though it looks more and more like we're trending toward an adaptivist angle. Geoengineering until very recently was not taken particularly seriously as a legitimate third strategy here. It was sort of fringe. The impression was that these are sort of high in the sky, science fiction-y ideas that involve us doing bizarre things like shooting mirrors up into space to block out the sun's rays. And until really the last 10 or 15 years, this hasn't gotten a whole lot of play in either the scientific literature or in popular media. There are a couple of different reasons for that. I like to think that the most optimistic one is that everybody thought that by the time we got to this point, we would have solved it. We would actually have some sort of strategy that we had agreed upon and that was on the table that would let us mitigate this stuff, and it would never come to this. But as that has continued to not happen, as we're getting closer and closer to that 2 degrees Celsius danger zone that people are concerned about, this has become more and more an object of attention. The more recent IPCC report, the one that came out last year or the year before, for the first time had a really significant section on this. There was a 50 or 60 page analysis. They convened their own special working group to talk about geoengineering. So some of you, if you guys watch Bill Maher on HBO, he had Bill Nye, the science guy, on a couple of weeks ago, maybe last month. And Bill Nye was actually talking about this, and he just said, you're all freaking crazy, like nobody would want to do this. It was a Newsweek cover story back in December. So all of a sudden this stuff, basically since I've started working here, which I take all of the credit for, has kind of exploded into popular consciousness. People are thinking about this in a way that they hadn't been in a serious way before. So for the purposes of our discussion, here's what I'm going to mean by geoengineering. I'm a philosopher, so we have to give a lot of definitions of things. Geoengineering is deliberately pursued as a response to climate change and not as a side effect of another activity. So if we do something like, I don't know, set off a nuclear weapon, or if Iran bombs somebody and kicks up a whole bunch of dust into the atmosphere and we get a nuclear winter, that's not going to count as geoengineering on this view. I'm interested in stuff where we're doing this sort of thing deliberately. Those kinds of interventions, but cases where we're doing it on purpose and not by accident. It's also designed to produce an effect that's global in scope and capable of impacting the climate on pretty long timescales. For this to be a serious option, it's going to have to be at least years, because that's how long it's going to take us to sort of step things down in terms of mitigation or adaptation. So doing something like erecting a biodome out in the Mojave Desert and then going and living there, even though it's changing the climate for a long term, very locally, that's not going to count for the kind of thing that I'm interested in either. And the third definition primarily involves interventions in the functioning of geosystems rather than human institutions, behavior, or other kinds of natural systems. Just yesterday, I saw there's a new paper up on the archive. For those of you who are science people, you know what that is. It's a preprint server where people put up their publishing papers before they go to print, where some people at one or another complex systems institute, I think it was in New England, proposed that we could do genetic engineering and build new and better bacteria and release them into the world. And they would uptake carbon dioxide in a way that was more efficient than some of the bacteria that's around right now, and that would help things out. So that's a kind of geoengineering, but it's not the sort of thing that I'm interested in here.